reactivity. So, we will still continuing with the mechanisms which can talk about the different types of reactions, and these reactions particularly happening when a metal is reacting directly with the ligands. So, today we will be talking about the reaction mechanisms part 3, and in which particular mechanism we can use for two types of reactions. Some reactions are can be categorized as slow, that we have seen in our last class, and some of these reactions we can consider as first reactions. So, it is the inherent property of the metal ions as well as the ligands which can show some of these reactions. So, when we have the slow reactions, we basically label the corresponding complexes which are participating in these slow reactions as some inert complexes. So, these inert complexes are definitely go for only slow kinetics, irrespective of its thermodynamic stability or instability. They can go for only slow reactions when these reactions are very slow in nature, and several metal ion configurations such as D3, low spin D4, D5 and D6 will consider that these metal ions can give rise to very slow reactions, and the corresponding compounds we can call as inert metal complexes in terms of their ligand substitution reactions, as well as some of them in strong field with D8 electronic configuration. Definitely in strong field D8 configuration, most of the cases we get the square planar complexes such as several platinum and palladium compounds. So, this D3 electronic configuration we all know that this is for chromium 3. So, if we have the corresponding chromium 3 compound, and if we have only 3 unpaired electrons on the chromium orbitals, the d orbitals, then this can react very slowly for the ligand substitution, even for the water exchange reactions. Similarly, for D6 configuration we have the cobalt, the trivalent cobalt, which we have seen also in case of the corresponding hexaamine cobalt 3 compound, which is substitutionally inert, and when this compound is reacting with acids, say protons, giving rise to the corresponding substitution of all the ammonia ligands by water molecules to give us the corresponding hexa-aco cobalt 3 compound and 6 ammonium ion after protonation. This compound is unstable in acid, but reacts very slowly with this acid. Very slowly with the acid. So, even we are considering the corresponding reaction of this, that means the proton is attacking the corresponding ammonium ligands forming ammonium ion. Basically what we are going for, we are basically going for the corresponding substitution reactions where all the cobalt nitrogen bonds, we have 6 cobalt nitrogen bonds from the ammonia ligands attached to the cobalt center, are substituted by cobalt hydrogen attached to oxygen and then cobalt to oxygen, that means the cobalt oxygen bonds of the cobalt ACO group. So, these are reacts very slowly and therefore, we can label this as the inert compound. So, this is there then for the strong field D8 electronic configurations we can have. So, we can have platinum 2 for this particular one where is D8 configuration, and for this D6 configuration we can have platinum 4, platinum in +4 oxidation states. So, this basically gives us some idea that what are the different types of reactions we can consider as the corresponding slow reactions, and therefore, the other metal ions which are D1, D2, then not low spin, but high spin D4, D5 and D6. These can give rise to first reactions as well as D7, D9 and D10, which is the zinc 2 plus. So, in this particular case where we have these metal ions and the metal ion configurations can tell us that the reaction would be first, that means the corresponding complexes are labile in character. So, these two extreme ranges we can have. So, one is the slower range and another is the corresponding faster reactions, but as some of these molecules can also come as intermediate between these two ranges. So, the metal complexes which can show some intermediate reactivity pattern or reaction rate. So, kinetics are telling us that it will have some intermediate rate of reaction if we consider it as for the corresponding ligand substitution reactions. And already we have considered this as the strong field D8 system, but in this particular case we have the weak field D8 system such as nickel 2 plus. Nickel 2 plus in the corresponding tetrahedral geometry we get is a corresponding weak field D8 system, and that gives rise to the corresponding intermediate reaction rate for its corresponding ligand substitution reactions. So, what we will see that during these reactions we can have two different types of reactions. One is the associative, another is the dissociative reactions. So, whatever we are talking about here is the corresponding mechanism of substitutions. So, if we have the corresponding mechanism of substitution and we are talking about some of these ligands. So, the ligands will come. So, you can consider it as the corresponding ligand substitution reactions around the metal center, and when we add the stoichiometric amount of metal and the ligand, we have the stoichiometric mechanism. So, whatever mechanism we can have is based on stoichiometric amount of the addition of the ligand to the metal center. So, in one case we have the intimate mechanism. So, we have the intimate mechanism of reaction and we can have the dissociative, that means one ligand is going away, and the associative one, the reverse one, when one ligand is attaching to that particular system. So, if we are talking about the corresponding octahedral complex, so if one ligand is going away, so in the transition state we have a 5 coordinated system in the transition state of the reaction with that of the reactant. So, transition state reactants can give rise to a 5 coordinated system. So, for the associative reaction in the similar way we can have 7 coordinated transition state for the octahedral reactants, that means some ligand is reacting with the octahedral metal center. So, we can have two different types of activation, the dissociative activation and the associative activation, and we have the mechanism known as D, where we have in the extreme case we have the corresponding dissociative activation and we get the corresponding 4 coordinated compound. And at the other end we have the associative reaction for the extreme cases. So, these two, that means D and A, these are two extreme cases for these reactions. So, we have the associative versus dissociative reactions we can consider, and when we talk about the ligand substitution reactions, they can either be associative or dissociative. And when we have the associative reaction, just now we have seen that we can have an increase in coordination number. So, reaction intermediate, that means it leading towards the corresponding transition state, has higher coordination number than reactants or products. That means, if the reactant is octahedral in nature, we have 6 coordinated species, and if the product is also a octahedral one, the product is also 6 coordinated, but the transition state is 7 coordinated. So, these particular types of associative reactions are possible when we have the complexes of lower coordination number. If the coordination number is less, it can accept one more bond or two more bonds to form the higher coordination number for the transition state, and rate depends on the entering group. That means, the group which is coming and attaching to the metal center will control the corresponding reactivity pattern as well as the rate of the reaction. Similarly, when we go for the corresponding dissociative reaction, the reaction intermediate has lower coordination number than reactants or products. It is typically opposite to that of the associative reaction, and octahedral complexes can give rise to the dissociative reaction, and smaller metal centers, that means the metal centers having less coordination number compared to octahedral also, and in this particular case the rate of the reaction is dependent on the leaving group. That means, the group which is leaving to give rise to the 5 coordinated species will control the rate of the reaction. So, when we have these two, that means D in the extreme end and A in the other end, we have two other intermediate reactions which is known as intermediate dissociative as well as intermediate or interchange associative. So, one is I small d and I small a, and this I is the interchange. So, we can have in these two particular cases, when the incoming ligand is presumed to assist the reaction, but no detectable intermediates appear. So, no detectable intermediates appear. That means, the transition state has not very much half life to corresponding appearance and as corresponding detection in the corresponding state. So, in the case of the other one, that means ID, the degree of assistance is small and the reaction is primarily dissociative. So, the reaction what we get from there is primarily dissociative in nature, primarily dissociative in nature. So, when the incoming ligand in case of this IA, when the incoming ligand begins forming a bond to the central atom, that means intermediate associative, that means some weak interaction is taking place, the central atom with that central atom before the departing ligand bond is weakened appreciably. So, one bond is forming weakly to the metal's ligand when L prime is coming, and the other bond which is already present is there, which is weakened appreciably. So, this ligand metal bond will be weakened appreciably compared to that particular bond which is forming in a newer way. So, there are many reactions which can be described as IA and ID mechanism rather than typical A and D. So, we can have, therefore, we can consider that we have the reactions which we can consider as D and A at two extreme ends, or the two intermediate cases IA and ID. When the kinetic evidence is present, products to association or dissociation, but detection of intermediates is not possible, we get either D or A or IA or ID. So, when we bring this, that means this L prime can be a capital Y. So, we can have the different kinetic experiments, and that kinetic experiments can consider that large X of the incoming reagent Y, that means if this is X and the incoming reagent Y is there, then we can analyze the kinetic data for the progress of the reaction for a particular kinetic run. So, we use the kinetic run of the reaction, which will consider that it also dependent on the temperature of the reactions at different concentrations. So, initially when we consider the rate of the reaction, how it is affecting when we consider that different concentrations of Y can use different concentrations of Y, then what we get? We get the corresponding order of the reaction with respect to Y. So, if we are able to find out the corresponding order of the reaction from the kinetic data, we can find out that how the variation in the concentration of Y can affect the rate of the reaction, and whether this Y, that means the term, the concentration term Y is involved in the corresponding rate law for the corresponding reaction. So, we can have from this kinetic run, we have the kinetic rate law and the kinetic consequences of reaction pathways. So, whatever we are talking over here is the different reaction pathways. So, we want to know what particular pathway is giving a particular type of product. When you do a particular reaction, say M plus L, and if we can have different pathways for the reactions to take place where L is reacting with M, then we can find out the corresponding possible reaction pathways and its corresponding kinetic consequences, and we try to find out the corresponding kinetic rate law. So, the how this rate law can help us in understanding the corresponding values for these reactions, where we can consider that the reactivity pattern for a particular metal ion with the different ligands are different. So, the different patterns what we can see that the formation constant tell us about the thermodynamics, that means the K value, the equilibrium constant or the formation constant values tell us about the corresponding thermodynamic stability of the metal complex. So, if we have M plus Ln or ML6, we can determine the corresponding equilibrium constant or the formation constants for the different steps, that stepwise formation constants for the thermodynamic parameter, that means the equilibrium constant value as well as the corresponding delta G values. But in case of its corresponding formation rate, the kinetics for this particular reaction requires a different measures, where we consider the nucleophilicity, how it is looking, the ligand, how it is looking for the metal center, which is the corresponding nucleophilic center. So, the nucleophilicity, how we can consider for the corresponding kinetics of the reaction. So, in all these cases, the ligand displacement reactions are nucleophilic substitution reactions. So, one L is substituting other L which is attaching to the nucleophile, that means the corresponding metal center. So, we get the corresponding nucleophilic substitution reactions for these ligand substitution reactions. So, we have the rate of attack on a complex by a given ligand, that means the Lewis base is attacking the corresponding metal center relative to the rate of attack by a reference base. So, if we consider, that means if we just simply consider the corresponding substitution reaction, where the given ligand is our say ammonia, which is a Lewis base, and the reference ligand which is also a reference base is the water molecule. So, if we can go for the substitution of these water molecules for the metal aqua bond by the metal amine bond, how this particular new Lewis base can attack and remove these water molecules from the metal center, that we can find out, and how quickly they are happening, that we can find out from the corresponding rate of the reaction. So, in this particular case, so we can have two different reactions, one is the slow reaction and another is the corresponding fast reaction. So, the different rates which can span from 1 millisecond to 10 to the power 8 second. So, when we have 1 millisecond to the 10 to the power 8 second, which is in the lower range to the higher range. So, in this particular window we can measure the corresponding reactivity pattern, that means the rate of formation of the product and its corresponding dissociation by some mechanism. So, this particular thing can give us that ligand levels we can have, and these ligands we can use for its corresponding nucleophilic substitution reactions. So, three types of ligands we can consider, that we have the entering ligand Y, we have the ligand which is leaving from the system as X, and the spectator ligand which are present there as L. So, we can have the kinetic information for the different cases, and we can use to find this kinetic rate law for the different types of mechanisms. So, if we have a corresponding system like ML5, where X is present over there, which will be the corresponding leaving ligand. So, Lx can leave the system, which is leaving ligand, and this mechanism is dissociative in nature, that means the mechanism is D, and we can have two ways of this reaction for this dissociation, where we get ML5, where L are the spectator ligands and X is completely dissociating from the system. So, we can have a very small concentration, what we can assume as this hypothesis for a steady state approximation that this can have a very small concentration with the progress of the reaction. Then this ML5 can react with Y, which is our entering ligand. Y is our entering ligand, and this is also forming ML5Y. So, the rate of formation of this ML5 and ML5Y, all these are dependent on the rate of this particular dissociation, that means K1, and reverse of this reaction is K minus 1, and the rate of this particular attachment of the entering ligand is K2. So, this particular thing ultimately gives rise to the corresponding manipulations and all these giving us the corresponding rate law as d dt of the corresponding ML5Y. That means, the formation of this the product ML5Y with time. So, the formation of this, the rate of change of concentration of the new compound which is forming through the introduction of Y is therefore is dependent on K2, K1, these two K2 and K1 is dependent on these two steps, and the concentration of ML5X and the concentration of Y. So, in this case, that means for the dissociative case, it is dependent on the concentration of the compound which is reacting as well as the corresponding concentration of the entering ligand, and the corresponding decrease in concentration of this dissociation is the K minus 1 X plus K2 Y. So, this particular rate law is critically giving us the corresponding rate law for this dissociative mechanism. So, we have therefore three different types of ligands, which is entering, which is leaving, and which is there remaining as the spectator ligand. So, this species that neither enters nor leaves, what are these spectator ligands? So, spectator ligands are those ligands which is not entering into the system nor leaving the system, and particularly important when we find them as located in a transposition designated by T. This will considers in some way that when we are talking about the corresponding substitution reaction in octahedral complexes, we do not find any effect from the corresponding spectator ligand, but for the corresponding square planar complexes like that of our platinum or palladium, or for some strong field ligand around the nickel center like cyanide, we have these ligands which are trans to that particular system. That means, whether that particular position is the leaving position or the position is utilized for entering the ligand, trans to that, and these spectator ligands we can consider as the T ligand, which can see the corresponding reaction and can control the corresponding reactivity pattern for these centers. So, when we have, since we are talking about the stoichiometric reactions and the stoichiometric mechanisms, what we can see. So, we have this associative in 2 steps and dissociative in 2 steps, and the interchange which is a continuous process. That means, at 2 extremes what we have seen just now, that associative thing we can consider at one end and dissociative in the other, and in between we have the interchange of the corresponding mechanism. So, the rate determining steps which are very important, how we can find out from the rate law in case of associative mechanism, the rate depends heavily on the entering group. The group which is entering is dependent on that particular concentration. That means, when we go for the two ligands, the ligand which is coming up, which is being associated to the metal complex to giving a same coordinated intermediate, or after dissociation it is coming and attaching to the metal center. So, if the rate of the reaction is dependent on the entering group, we can consider that the mechanism of the reaction is associative in nature, and if it is dissociative, the rate of the reaction would be independent of the entering group. So, it will not be dependent on the corresponding entering group, and we can have this corresponding reaction which is dissociative in nature. So, principal binding mechanism for this, that means the mechanism for the ligand exchange in octahedral complexes, we can have that therefore, the dissociative one, where we have seen already, that is the K1, and the reverse of this we can consider as K minus 1, and when it is only a dissociative one without involvement of the Y, the rate is straightway dependent on K1 times ml5x. That means, in this particular case the rate is independent of Y, and we can consider it as that the second step, that means the contribution for this K2 step, the rate which is dependent on the corresponding rate constant K2 is very fast. So, immediately wherever the ML5 is forming, it immediately reacting with Y, forming ML5Y, and in that particular case, if this is pretty fast and we are unable to measure the corresponding K2 value, the rate of the reaction R will be only dependent on the concentration of ML5X without giving rise to the corresponding concentration of Y into the detailed rate law for the corresponding reaction of dissociative type. So, in the other case, which is associative in nature, that means where the incoming ligand can go and attach to the metal center, forming the ML5XY. So, in this particular case, this is the slow step, this is also the slow step, but in this particular case the dissociation is the slow step or the slowest step, and the slowest step is the rate determining step. That means, the rate of the reaction is dependent only on the slowest step, that means the dissociation path. Similarly, since this is the slowest step, that means the rate of the reaction is dependent on the associative pathway, which is dependent on the rate constant K1. Therefore, the rate equation in this particular case would be R is equal to K1 into ML5X into Y. That means, it has the contribution of both the two, that means the concentration of the starting complex, that means ML5X, and the concentration of the entering group, that means the Y. When both these two concentrations are involved over there, we can consider it as some kind of associative mechanism is operating, and the second step for the removal of X is very fast. So, it has no contribution. So, in the rate law there is no contribution for K2, but for some other cases where we consider as the interchange for these reactions, that means IA or ID, whether it is associative interchange or dissociative interchange, we can have the corresponding reactions where the rate law can involve both K1 and K2 as well as the concentration of the intermediate as well as the starting compound and the product concentration. So, we see the corresponding energy profile, how we consider it as the corresponding free energy change for these reactions. So, the free energy change for the reaction, this is L5 has not mentioned over here, this is ML5X, Y is there, then ML5 plus X plus Y as the intermediate, where it is a dissociative pathway, that means ML5 is forming and ML5 will have some stability at this particular point. So, this this particular stabilized point has Ml5, that means the dissociated form has some stabilization, then it is reacting with Y forming the product which is Ml5Y. Here also due to the extent of reaction the associated form has some stability. So, if we are able to detect this, if we have certain stability for this, that means the steady state approximation was not valid in this particular case, where we are not assuming that these two intermediate has very low concentration, but it has certain amount of measurable concentration, then we can have the corresponding intermediates and we can involve the corresponding rate law for the involvement of these species for the progress of the reaction. So, this one, that means the dissociative pathway is the most common one, where this Ml5x is reacting with Y giving Ml5y plus x, and is a 5 coordinate intermediate in this particular case, and in the other case we have the 7 coordinated intermediate is forming, that we have discussed so far, and the corresponding free energy and the path for the corresponding extent of reaction can also be monitored in that way for to find out the corresponding rate law. This we have already discussed in detail, that means how we can consider the different inert and labile complexes. One is the corresponding thermodynamic part and another is the corresponding kinetic part. So, when we have these things, that means the corresponding reactions, one is we are considering as the dissociative path, another we are considering as the corresponding associative path. And when we consider these reaction profiles, such as when we have this particular case as D, we can also the reaction as the corresponding associative pathway, where Ml5x is reacting straightway with Y and both way reaction can give rise to Ml5xy, that means the associated form. We have this K1 and K minus 1 in the same way as that of our dissociative pathway. Then in the second step, this particular associated form, that means Ml5xy, is going for the elimination of the x, giving rise to Ml5y plus x. And the rate of the reaction, the rate law for the reaction, that means d of Ml5y dt would be equal to K1 K2 again Ml5 x y and K minus 1 plus K2. So, this particular rate law can also be considered when we have very small values for this K minus 1 and K2 values. These are the very first reaction, and when we consider that this particular one, when these are very small, this K2 and K2, this is very small, K2 and K2 can cancel out, and we can have for all these products we can have the corresponding one constant which is K, which is Ml5x and y. So, this particular case also the rate law is dependent on both the concentration of this particular species and the concentration of the corresponding incoming ligand or the entering ligand which is attaching to that particular metal center. So, where we see that due to these two, that means the D and L, we can have also this intimate reaction where the interchange is taking place, where we have I A as well as I D. So, dissociative interchange and the associative interchange. So, this associative interchange is taking place if the breaking of the bond between the living ligand and the metal is important. So, bond breaking is important in this particular case. And in the second case, which is the dissociative one, where the bond formation, the bond between incoming ligand, that means bond between incoming ligand and the metal is important. So, for these different types of reactions, we just now bring the corresponding temperature parameter. So far we are talking about the corresponding rate law and the concentration change for the different reactive patterns, that means the corresponding X concentration and the Y concentration, the leaving ligand and the entering ligand we are talking about. Now, if we consider the temperature, we can have the corresponding Arrhenius equation. So, Arrhenius equation can play some important role over there, where the rate of the reaction K is equal to A e to the power minus E A by R T. E A is the energy of activation and K is the rate of the reaction and A is the constant, or ln K is equal to ln A minus E A by R T. So, these basically gives us some of these plots where we can find out that how the corresponding parameters, that means where the K values we know that these are the rate of the reaction which has some dependence on the thermodynamic stability for the corresponding K value, that means K forward reaction divided by K backward reaction will give us the corresponding equilibrium constant value. But this particular E A value is nothing but the corresponding energy of activation in the corresponding potential energy barrier. How quickly we can cross the corresponding energy barrier in terms of the energy of activation, that gives rise to the corresponding rate of the reaction. So, we can have three different types of these plots depending upon the E A is a small a, definitely is a energy of activation with respect to the enthalpy of the reaction. If the enthalpy of the reaction is less, that means delta H is less and which is less than 0, we can have a corresponding large equilibrium constant, because we know that if we have delta H is less than 0, we can talk about the corresponding delta G also, because this delta G is related to delta H through T delta S, and the temperature effect is on the entropy term, but this corresponding heat of reaction is directly related to the corresponding free energy change of the reaction. And if this is negative also, this is less than 0 or negative. So, we can have the corresponding K value which is the equilibrium constant, and this equilibrium constant would be large. So, we have large equilibrium constant. So, whenever we have this delta H less than 0, our delta G is also less than 0 and we have large equilibrium constant. So, in these first two cases where we have this delta H is small, here also the delta H is small. So, we have this large equilibrium constant, that means it has the thermodynamic stability. That means these two cases we are considering as the stable complexes, stable metal complexes. But when we talk about its kinetic profile, we should consider its corresponding the EA values, the energy of activation, how much you have the corresponding barrier to cross from the left hand side, which we have considered so far as ML5X, to get ultimately to ML5Y, that means the corresponding product formation. So, this is the corresponding barrier where it has to be crossed such that you can have, in some cases you can have the intermediate, and in some other case you do not have the intermediate. That means, if it is the going through the dissociative mechanism, we have the corresponding dissociated form, that means the 5 coordinated species is the intermediate. But if it is the associated form, that means the 7 coordinated species would be the intermediate. But these two cases the EA values are large, that means we get the corresponding reactions for these as the very slow reactions. So, we get the very slow reactions for these, though kinetically they are very stable. So, it has large equilibrium constant. So, thermodynamically they are stable, but it is very slow reaction. So, it is a very inert compound. So, the complexes are typically inert. But in this particular case, we have both these cases, we have in this, because delta H is greater than 0, delta H is positive, that means when the delta H is positive is greater than 0, delta G is also greater than 0 or positive. So, when delta H is greater than 0 and delta G is positive, so we have the corresponding K value, that means the equilibrium constant is therefore small. So, it is thermodynamically not very stable. So, it is thermodynamically unstable compound, but what about its corresponding energy of activation? This EA value compared to these two is also small. So, your corresponding barrier for activation is also small. So, if the barrier of activation is small, we get a corresponding very fast reaction. That means, it is therefore a corresponding labile compound, it will react very fast way, and the rate of the reaction is also very fast. So, the energy of activation is giving us some idea that whether this particular reaction can give rise to the corresponding separation for these two cases, that means the corresponding energy of activation, and that energy of activation can give rise to the corresponding these two thermodynamic and kinetic parameters. So, we find that in this particular case we have this exothermic one, which is favored as large K and large EA, therefore, we have a very slow reaction. In the second case, we have this is also exothermic favored by large K, large EA, slow reaction, but it has some stable intermediate. The difference between A and B is nothing but here we do not have some depression and we have no such stable intermediate, but here in this particular case we have some stable intermediate. So, we can consider, though everything is same, but we can consider that the type of or the nature of the reaction is different, because in this particular case we have the stable intermediate. And in the third case we have endothermic reaction, because your delta H is greater than 0 and therefore, the reaction is disfavored, which has a small k value. Small k value also tell us about the corresponding positive value for the free energy change, but at the same time our EA value, the energy of activation, is also small and we get a very fast reaction. So, this basically gives us some important idea about the different types of reactions. So, if we have certain reactions, so we have some slower ligand exchange rates we can consider, and which is dependent on the oxidation states. So, depending upon the oxidation states, we have very slower ligand exchange rate than the rate of the reaction for the water exchange also and other ligands. So, if it is dependent on simply the oxidation state, therefore, the rate of the reaction is greater than for hexafluoroaluminate to Si(X)2 minus, where we have the corresponding oxidation state is different, then PF6 minus, which is greater than SF6, where 6, 5, 4, 3. So, where we have this particular one, where we have the higher oxidation state, where the corresponding rate is also slow. Similarly, for the water exchange reaction, for this also can change. For monocationic sodium, which is higher than that of our magnesium aqua compound, which is bivalent and which is greater than that of our aluminum 3 plus. So, as we change the corresponding oxidation state, so rate of the reaction is also decreasing, and we have the highest possible rate of exchange, ligand exchange, whether it is the fluoride exchange or water exchange, is for the other oxidation state. And similarly, it has also dependence on, this is case 1 and this is case 2 for ionic radii. So, we can have the ionic radii for strontium, we can have the ionic radii for calcium, and we can have the corresponding ionic radii for magnesium, and all these has some particular order. So, if we consider the corresponding rate for this exchange reaction, so the smaller ions, so those ions which are smaller, that means magnesium is smaller than calcium than strontium. So, smaller ions have slower exchange rates. So, the smaller ion is magnesium hexaco, which is 66 picometer only, which is less than calcium 2 plus, which is 99 picometer, and then strontium, which is 112 picometer. So, if we just consider the corresponding water exchange rate, the rate of water exchange we can consider for the water molecules which are bound to the metal ion, to the bulk water molecules which are surrounding the system, and if we can sometime level this water, this H2O can be leveled by O18, and we can some experiments which we can consider that how this leveled water can exchange with these metal ions. So, it is typically dependent on the corresponding oxidation state, and we can find out that depending upon these, basically where we can have the corresponding strong metal oxygen bond, and if the nature of the metal oxygen bond can predict some of the strength for these metal oxygen bonds and the corresponding rate of the reaction. So, in our next class we will consider about the corresponding effect for these trans ligands, how it can control the different rate of the reactions. Thank you very much.